Good evening, everyone. Welcome to week 7 problem solving session for analog electronic circuits course. We have already finished the first half of the course, moving on to the second half. Today we will be talking about multi-stage amplifiers based on BJTs and MOSFETs. Moving on to the first problem. In this problem, it is given that VBE is 0.6 volts, for both the transistors. VC is 0.3 volts. Beta is 180 and VCC is 12 volts. With this we have VT of 26 millivolts, R1 is 12 kilo ohms, R2 is 3 kilo ohms, RE is 1 kilo ohm, R3 is 3 kilo ohms, R4 1.2 kilo ohm, C1 and C2 are 10 microfarad each. CL is 100 picofarad. With this, it is given that C1 is ideal, so that is, we are not considering the effect of parasitics in Q1 first transistor, and for second transistor we have C pi of 10 picofarad and C mu of 5 picofarad. So with this information, we'll move ahead. Okay, so here we have to find the DC voltage between collector and emitter terminal of Q2. That means we have to find this voltage, that is VCE. So how can we find VCE? If we look at this particular path, we can say VCC equal to VC plus IR4, right? So the moment we know IE2, we can simply find out this drop across R4 and we'll find. Hi Vasanti, I just started. Do you want me to repeat it again? Maybe we'll go through the question again, okay? So, can you hear me? Am I audible clearly? Hello? Vasanti, can you hear me? Hello? Hello, Vasanti? Hi, can you hear me? Maybe you can write it down in the chat if you are able to hear me or not. Okay, you are able to hear me. So do you want me to go through the problem again? So today we will be solving the problems based on multi-stage amplifiers for both BJTs as well as amplifiers, MOSFETs, okay? So this first problem is a BJT based problem where we have a CECC amplifier. Good evening. Yeah. So this first stage is CE stage, whereas the second stage is a CC stage, right? Okay. So in this particular stage, I just defined that what are the givens in the problem. So we have all the resistor and capacitance values given to us. We are considering that Q1 doesn't contribute to any parasitic capacitances, whereas Q2 has C pi and C mu values. As you can see, I have written on the circuit. Now, other than that, we have the values like VB1, VB2, We see sat for both the transistors, betas for both the transistors, and now we have to actually find out what is the VCE across the second transistor. That is the task. So what we have to do is we have to find this VCE. So for that, how can we find the VCE? It is, see, if we look at this path from VCC to ground, we'll find that it can be written as VCC will drop across our VCE, that is transistor is VCE, and then it will drop across this resistor R4, right? So, and across resistor, the drop across resistor, we can simply write it as IE into R4, right? So if we find this IE, we can find this VCE. So VCE2 is VCC minus I2 R4, right? So our target is to find I2. Yes, this is week 7. Okay. So the target is to find IE2. Now how will we find IE2? So in this particular circuit, sorry, this voltage VB we can find out, right? We'll start from previous stages and we'll move one by one to the final stage. So for this stage, VB1 is 12 into 3 upon 3 plus 12. So here we'll get 12 by 5, which is, yeah, so VB1 is 12 by 5, so it is 2.4. We have VB1. We know VBE, right? So VBE we know 0.6 volts. So if we want to calculate the current IB or IB1, we can write it as VB1 minus VBE1 upon RBB base resistance plus R pi plus 1 plus beta 1 into RE, right? This is how we can write the expression for the current across the first transistor, that is base current across the first transistor. So here, if we see carefully, the base resistance RB and R pi will be very small compared to beta times of RE. Since RE is 1 kilo ohm and beta is 180, so it is 190 kilo ohms, which will be much higher than RBB plus R pi, right? R pi will be a small value and RBB is like the combination of these two, R1 and R2. So it is much greater than RBB plus R pi. So we can carefully neglect this one and we'll write IB1 as VB1 minus VBE upon 1 plus beta 1 into RE. So it is 2.4 minus 0.6 by 181 into 1 kilo ohm. So it is 1.8 by 181 milliamps. So how much will be IC1? It is beta times of IB1, right? So it will be 180 into 1.8 upon 181 milliamperes, which is close to 1.8 milliamperes, right? So we have got the current IC1 flowing through this transistor. Now since we have got IC1, so now what we will do, we have got IC1. Now for VC1, if now this voltage is required for me, right? How can I find this voltage? This is VCC, this is R3. Considering the current flowing through this transistor, Q2's base is very small. What we will do is, we will considering the base current through this transistor is very small, we'll neglect that part and we can find VC1, that is collector voltage of transistor 1, as VCC minus IC1 into R3. So it will give the drop from this point to ground. So VC1 is 12 minus 1.8 into R3 is 3 kilo ohms. So R3 is 3 kilo ohms. So we have VC1 is 6.6 volts. Now this VC1 will act as VB for Q2, right? For Q2, VC1 is VB2 for Q2. Now for IB2, how we will write? For IB2, we will have VC1 or VB1. We can write anything. So let's go ahead with VC1 minus VB2 upon R3 plus R pi 2 plus 1 plus beta 2 into R4. So here again we'll consider the same assumption that R3 plus R pi 2 is much less than 1 plus beta 2 into R4. So IB2 we will get it as VC1 minus VB2, so it will be 6 volts. 6 volts by 1 plus beta 2 into how much is R4? 1.2 kilo ohm. So that is 5 milliamperes by 1 plus beta 2. So IE2, how much will be IE2? It will be 1 plus beta 2 into IB2, right? So it will be 1 plus beta 2 into 5 milliamperes by 1 plus beta 2. So we will get IE2 as 5 milliamperes. So with this, now since IE we know, we'll put it in the very first equation that we said we'll use, and we'll get the final VCE. VCE is 12 minus 5 into 1.2. So VCE2 is 6 volts. Okay. So after this, we'll move on to the next problem. So in this problem, we have to find the overall gain in the mid-frequency range. Mid-frequency range means the range where the gain is considered as constant in the frequency response, right? So this is how the frequency response looks like. So in this particular range that we consider the constant gain, in that range we have to find the gain. So mid-frequency range of the amplifier circuit as shown in the figure. So how do we find the gain? Since it is a multi-stage amplifier, we have two stages, so two gains will simply come into picture. We have the gain, that is gain from stage 1 multiplied by gain from stage 2. Is this it? So the answer is no, this is not correct, because in case of BJT, due to this low base resistance or low input resistance, there is a loading effect that can be seen for stage 1 due to stage 2. So because of this loading effect, we'll see another factor over here which comes into picture due to loading effect that will also play the part in the gain. Okay, so now if I want to write the gain of first stage, which is a CE amplifier. What is the formula for gain of CE amplifier? It's simply GM1 into RL, right? For RL here it will be R3. Simply GM1 into R3. Now for second stage, what is the second stage? It is a CC amplifier. So the gain for CC amplifier is 1 plus beta 2 upon 1 plus beta 2 plus R5 by R4. Yeah. This is the gain for stage 2, that is CC amplifier. Now what will be the loading factor? The loading factor is because of the input resistance R5 coming into picture and this R4 coming into picture in series with this R3. So the loading factor will look like R by 2 plus 1 plus beta 2 into R4 upon R by 2 plus 1 plus beta 2 R4 plus R3. So this is how we will write the loading factor. Now once we calculate all these three values, we'll simply substitute and multiply them. So coming back to AV1, so for that we have to find GM1. How do we find GM1? It is IC1 by V2. We have found out IC to be 1.8 millivolts, right? And VT was 26 millivolts. So GM1 turns out to be 9 by 130 Siemens. Sorry. Now we have found out the GM. Here we'll simply multiply the R3 of 3 kilo ohms and we'll get AV1 as 27 by 130 Siemens. Oh, 27 by 130 volts per. This is our AV1. Now for AV2, what do we need? We need to find this R pi. How do we find R pi? R pi is beta upon GM. So beta 2 upon GM2. For this we need to find GM2 first. GM2 is again IC2 by VT. IC2, how much was IC2? It was 5 milli, right? 5 milli by 26 millivolts. So it turns out to be 5 by 26 Siemens. So R by 2 is 180 by 5 into 26. 936. So R pi is 936 ohms. There. Here it was 3 kilo ohms, right? So that kilo will come into picture. So it's 700 by 1 by 13. And AV2 is, here this is R pi is 936. So now when we calculate AV2, it will be 936 plus 181 into R4 is how much? 1.2k by 936 181 1.2k plus R3 is 3 kilo. So AV2 turns out to be 9050, close to 9050 by 9089. That is what we get is AV2 volts by volts. Now we have to find for the loading factor. So for loading factor we already have R by 2. Oh, wait, R by 2 1 plus beta R4. Oh no, this is not loading factor. So this is not AV2, this is actually loading factor. Because R by 2 into 1 plus beta R4 by R by 2 1 plus beta R4 plus R3, right? So this is loading factor. And the value of loading factor is 9089 by 9214. And when we say AV2 is 1 plus beta 2 1 plus beta 2 plus R by 2 by R4. So it's 181 by 181 plus 936 upon R4 is 1.2k. So AV2 turns out to be 9050 by 9089. Okay. This is again volt by volt. So overall gain, V out by Vn is actually multiplication of all the three. So 2700 by 13 into 9089 9214 into 9050 by 9089. So this turns out to be around 204 volt by volt. So the overall gain is 204. Okay. Moving on to the next problem. Here we have to find the small signal output resistance of the amplifier circuit shown in the figure. So in this figure, we have to calculate the small signal resistance at this point. So what will be the small signal resistance at small signal output resistance? So this is a CC stage, right? So if I make a small signal model, how it will look like? Here we will have R4, this is emitter, this is R by 2, which is, this is base terminal, this is collector terminal, So it's GM VB. So यहाँ पे plus minus this is VB voltage, right? So when we want to see the output resistance, that means this is where we will be connecting Vx, external voltage source, and this is Ix. We will not consider this. And in this remaining circuit, we have to find what is the value of. So basically, we have to find Vx by Ix. That is the idea. And here, if we extend this part, we will see that after this intrinsic base resistance of transistor 2, we can also notice that there is our output resistance of stage 1 which will come into picture, which is over here. Now this voltage is Vx, that means this voltage is Vx. So here, this VBE is actually, this VBE is minus Vx. Why? Because the drop VB's polarity is different. So that's why it is minus Vx into r by 2 upon r naught 1 plus r by 2. Right? Now if we look into it very carefully, here we have Ix coming into picture, and from here we have GM coming into picture. So this Ix plus GM VB is going into this path, into this particular path, right? So this path, the current in this path can be written as Vx upon r naught 1 plus r by 2, right? Now here in place of VB, we can substitute it with this. So we will have Ix equal to Vx 1 upon r naught 1 plus r by 2 plus r by 2 upon r naught 1 plus r by 2. So that is Vx upon Ix is r naught 1 plus r by 2 upon r by 2 plus 1, right? And in this, now this is R, let's say RE2, okay? And so here if we apply Vx will have some part going up, some part going down also, right? So this resistance and where did the beta go? Here we'll have beta GM as well, right? So this GM also will come into picture. So yeah, here we have GM r by 2 and r naught r by 2 and then r by 2 and r by 2. So GM into r by will eventually become beta. So this becomes r naught 1 plus r by 2 by 1 plus beta, and actual R out will be Re2 parallel to R4. So this Re2 is actually 3 kilo ohms plus 936, which is R5 by 181, parallel to R4 is 1.2 kilo ohms. So this R out actually turns out to be 21.4 ohms, around 21.4 ohms. This is the R out that we observe from the output of CC stage. Now moving ahead, we have to find the upper cutoff frequency of the amplifier. So for the upper cutoff frequency, what we will do? How do we find upper cutoff frequency? For frequency, we know it is 1 upon 2 pi R into C. We have to go to the different nodes, and we have to calculate the R resultant R and C over there, and from there we will decide which pole will actually contribute to the upper cutoff or lower cutoff frequencies, right? So here, let's look at this output node first. Node A, let's say. So for here, the frequency at A will be 1 upon 2 pi into R0 into CL, right? So R0 we have already calculated, it is 21.4 ohms, and CL is 100 picofarad. So we will get and this is around 74.37 megahertz. Now, which else is the node which can contribute to this node, right? Let's name it as node B. So here we will have 1 by 2 pi into R. So what will be the resultant R? It will be R01 coming from first stage parallel to Rn2 coming from the second stage into, now when we talk about C, so here see we don't have any coupling capacitors or anything, right? So it will be majorly based on the intrinsic parasitic capacitances. It's already mentioned that we should neglect the intrinsic capacitances for stage 1. So there will be the contribution of intrinsic capacitances from stage 2 only. So we will have C pi. So how does C pi and R pi appear? We need to know that first. So C pi appears between base and emitter, right? We have C pi between base and emitter terminal, and we have C mu between collector and base terminal. Now depending on, so here the question is, first of all, which capacitor is a Miller capacitor? Is it C mu here as well, which is a Miller capacitor? So the answer is no, because here if we observe, it is collector, base and emitter, right? So collector is fixed and it will be AC grounded. So at that point of time, that capacitor, which is C mu, it will appear completely in the base. So we will see a factor C mu, and it is not a Miller capacitor. Now which one is the Miller capacitor? It is actually the C pi that is appearing between base and emitter terminal, that acts as a Miller capacitor. So here C mu will appear, and in parallel to that we will have the component of C pi with 1 minus AV, that is 1 minus gain times. So the resultant capacitor over here will be C mu plus C pi 1 minus AV. So this is the resultant capacitor that we will observe at this particular point. Right? So now C pi is 10 picofarads and 1 minus AV. We know for the CC stage AV is close to 1. So 1 minus AV will be a very small value. So which makes this almost equal to C mu. So the resultant capacitor will actually be C mu. And we have to look into R01, right? So R01 is simply R3, which is 3 kilo ohms, which is parallel to R into that is R pi 2 plus 1 plus beta 2 into R4. So this is actually 218.136 kilo ohms, and here this is 3 kilo ohms. So when we go for 3 kilo ohms parallel to 218.136 kilo ohms, so it will be close to 3 kilo ohms. So your frequency at node B will be around 10.75 megahertz. Okay, now we have two frequencies at A and B. We need to find out which one to consider. It is asked that you have to find the upper cutoff frequency. So see, we know how does the frequency response looks like, right? This is how the frequency response looks like, and we have to find the upper cutoff frequency. That means a frequency which will be coming at this point. Now if there is a pole which appears at this point and there is another pole which appears at this point, what do you think, which pole will actually define your upper cutoff frequency? It is this pole, right, which will tell you about your FU. It is upper cutoff frequency. Now in the same terms, if I had to calculate lower cutoff frequency and I had two poles, one appearing here, one appearing here, so which will define my lower cutoff frequency? It is actually this pole which will define the lower cutoff frequency. So for lower cutoff frequency, it is the maximum of the two, and for upper cutoff frequency, it will be the minimum of the two. So our upper cutoff frequency will actually be the 10.75 megahertz. Since both are there, so we will go for minimum. This is actually minimum of frequency 1, frequency A and frequency B. I hope this is clear. With this, let's move on to the next problem. So in this problem, it is a theoretical problem. Here we have to define the advantages based on cascode MOSFET based amplifier over a CS amplifier. So what do you mean by cascode? Cascode means we'll add multiple transistors one over the other in a series format. It means so this is how a telescopic cascode looks like. Okay, so here we have P, P, N, N. In a CS stage, we have single N and single P, right? This is a PMOS and this is a NMOS. This is where we take output CS. This is cascode. And what about cascade? So if it is like CS, there are two CS stages such that the output from one is joined as input to the other. Then we call it as a cascade. So this is cascade amplifier. Here we have two CS stages connected back to back. This is cascade amplifier, where here we'll give the input and from here we'll take the output. Here this is where we'll give the input, and in this is where we give the input. So these are, so this is the CS that we have learned till now. After that, this is the cascade and this is cascade. So looking at the circuit, we have to say what is the advantage that we can get from this cascade amplifier. So first of all, if we look at it very carefully, sorry, if you look at this cascade circuit very carefully, here we won't find any Miller capacitor. What do we mean by Miller capacitor? A capacitor that is connected between input and output node. But here, since input and output nodes are far apart, so we'll not see any Miller capacitance effect. So it will actually, and Miller capacitance, what is the disadvantage that we get? It is actually the input capacitance that increases because of it being multiplied with the gain. So here, in case of cascade, the input capacitance actually reduces. That is because we don't see the Miller capacitance, and it is a significant capacitance that comes into picture, and which can be simply avoided using cascade. Now, what else is the advantage? So here, since we have two transistors in series, so it will increase this Z out, and which will finally increase the voltage gain of this particular transistors or this particular cascade amplifier. So another advantage that we get is voltage gain, which is being very high. And if we also look into this, that how many poles do we have? So here we will have 2 poles, 3 poles. Here we will have 1, 2 poles and 3. That is your input pole. So here if we look at it carefully, for the CS stage, these 2 poles are actually comparable to each other. And they are almost close by each other. Whereas in case of cascade, it is this pole whose resistance is higher because it is at drain, whereas these two are drain source connections. So these have lesser resistances. A and B have lesser resistances compared to C node. So C node will only contribute to the majority or to the what should I say, critical pole, and there is only one critical pole which will actually define the bandwidth of your circuit. So it also helps in the bandwidth, the cascade amplifier. But what are the disadvantages of having a cascade amplifier? As you can see, from VDD to ground, there are 4 transistors which are going to drop the voltage. So it is actually affecting the swing. So we will not be able to see a significant amount of swing in the transistors. So that is one disadvantage that we see from by using the cascade amplifier. Now moving on to the next problem. In this we have the voltage gain of C and CC amplifier with respect to C amplifier. What happens if there is a C coupled with CC and there is only a C amplifier? How do we see the change in the gain? As we have solved earlier also in the numerical, the gain actually reduces. That is because C has a higher gain and CC has a gain less than 1. So if it was product, even if it was product of the two gains, it would have reduced. But other than that, in C-CC combination, we also see a loading effect, and loading effect is always less than 1, right? It will give you a less than 1 factor, so it will deteriorate the gain even further. So what happens to the gain when we see a C-CC amplifier? It actually reduces the gain, so the gain decreases more. So this is the answer. Moving on to the next problem. In this problem we have to find the equivalent beta such that beta 1 is given to be 100 and beta 2 is also 100. Okay, so we know that I IB comes over here, right? And here we have IC. IC will be beta 1, beta into IB1, right? Beta 1 into IB1. And what about IE? For this Q1, it will be beta 1 plus 1 into IB1, right? Now this is entering as a base current for Q2. So now IB2 is actually beta 1 plus 1 into IB1. Now in case of IC2, how will the IC2 look like? IC2 is beta 2 into IB2, right? So the effective beta, when we say effective beta of this both circuits, it should be IB1, IC1, IC2 by IB1 will give us beta effective, right? So now let's substitute this in this. What we will see, IC2 is beta 2 into 1 plus beta 1 IB1, right? So IC2 by IB1 is beta 2 1 plus beta 1. So this is actually beta effective of the two transistors. It is the product of two betas. That is 100 into 101. So 10100 is the beta effective. Clear? So after this, let's move on to the next problem. Now these set of problems are based on CS and CD amplifiers, so basically MOS based amplifiers. So in this, again R4 is 4 kilo ohm, R1 is 4 kilo ohms, R2 is 12 kilo ohms, R3 is 4 kilo ohm, R4 is 1 kilo ohm, C1, C2 are 10 micro, 10 micro, and CL is 400 pico. Yeah, CL is 400 pico. CGS is 10 picofarad, CGT is 5 picofarad, and here it should only be considered for 2. It is M2. We'll neglect the intrinsic capacitances for M1. This is all it says, and with this it is given that lambda is 0, which is very good, and VTH is given minus 1 volt. Minus 1 why? Because these are PMOSes. And kW by L is going to be 1 milliampere per volt square. Now the question is, find the DC voltage, that is to say output voltage, between source to ground terminal. Yes, we have to find this output. How do we find this output? What is the thought process for this? So if we want to solve this, how do we solve this? So I want to find V out, right? So if I subtract VDD minus IDR4, I will get V out, right? So I need to find this ID2. How to find ID2? For that, see, for finding ID2, I need to know the value of VG2, and but VG2 is actually drain voltage. So for this I need to know VD1, and for knowing this VD1 I need to go from the very beginning and we'll start to find from VG1. So from VG1 we'll first find VG1, from there we'll find the currents, from there we'll find this VD say VG2, VG2 say we'll find the ID2, and from there we'll find the output. That is how the flow will be. So we have to actually flow in this way. We have to flow in this way manner, or it should actually be like this. Okay, so this is how we'll proceed. So first let's find VG1. How much is the VDD? Okay, VDD is 12. 12 volts. So VD is 12 volts. So 12 into 12 by 4 plus 12, it is 16. So 12 into 12 by 16, 3, 4, 3. So VG1 is actually 9 volts. Now VG1 we have found out. So VSG1 is how much? 3 volts, right? So considering the transistor N1 to be in saturation, assume N1 in saturation will have half kW by L VSG minus VTH whole square. So this is half into kW by L is 1 milliamps per whole square into 3 minus 1 ka whole square. So 2 square. So ID1 is 1 by 2 into 1 into 4. So it is 2 milliamperes. ID1. Now if this is the ID1, what will be this for VD? So it is ID into R3. VD will be ID into R3. R3 is 4 kilo ohms, so 2 into 4, it is 8 volts. So VSD is 12 minus 8, 4 volts. And since VSD is greater than VSG minus mod VTH, so yes, assumption is right. So saturation, T1 is in saturation, that is correct. Now we have found this VSD and we know VD to be 8 volts. This VD is 8 volts. Now since this VD is 8 volts, this is 12 volts. Now this is 8 volts. So let's again assume T2 in saturation. So the moment T2 in saturation, here ID2 is half kW by L VSG. So that is VSG minus mod VTH of whole square. Now it is not that straightforward as it looks like, right? Here we actually don't know what is this VS. VS is VDD minus IDR4. So VS is VDD minus IDR4 minus 8 volts of gate minus 1 volts of VTH of whole square. So ID is half kW by L 12 minus IDR4 in minus 9 square. ID is half kW by L 3 minus IDR4 whole square. So here we can clearly observe that we'll find a quadratic equation for drain current ID2. So once we solve this ID2, we can find the value of this VSD, or we can replace ID2 as VDD. See, ID2 can be written as VDD minus VS2 or VSD2 by R4. So we can substitute this over here and we can simply solve. That way also it will work. So here if we substitute and solve, we'll directly get the values of VSD. If we go ahead and substitute, so we'll get two values of VSD. One is the value is 10.65 volts and the other value is 5.35. Yes, 5.35 volts. And since VSG and VSD should be positive, so 5.35 will be discarded and VSD is 10.65 volts. Okay, so the VSD is 10.65 volts. Next problem. In this problem, we have to find the small signal output resistance of the amplifier shown. Yeah. In this, we have to see the output impedance on this side. So, if we look, so this is the source terminal, right? And source terminal, what is the RS or intrinsic resistance that we have for source? It is 1 by Gm plus G2. So here will be 1 by Gm2 plus 1 by Gm2 plus G2, right? And here we have R4. So actually Z out is R4 parallel to small rs 2 because that is for second transistor. So since lambda is 0, GT2 will be 0. We don't have to consider. So we need to find out GM2. GM2 is simply KW by L VSG minus VTH. We have found out VSG, right? So it's 1 milliamps per volt square into VS is 10 point, how much? 10.65 minus 8 minus 1, that's 9. So GM is 1.65 millisiemens. Now this is GM. So RS2 will be reciprocal of this. RS2 is 1 by 1.65 kilo ohms. And R4 is how much? 1 kilo ohm. R4 is 1 kilo ohm. So when they come in parallel, so the Z out turns out to be 1 kilo ohm parallel to 1 by 1.65 kilo ohms. So Z out will be 377 ohms. This is the value of Z out that we obtain when looking from the second transistor or from the output node. Yeah. Now we have to find the voltage gain in this problem. So here, first stage is our CS stage. So what is the gain for CS stage? AV1 is simply GM1 into Rout1, right? And when second stage is CD stage, the gain for CD stage is GM2 into R4 by, or we can write it like, okay, let it be GM2 into R4 by 1 plus GM2 into R4. Yes, so this is how it will look like. Now here, what is the Rout1? It is actually R3. So here in place of Rout1, we can write R3. GM1, what will be the value of GM1? So AV1 के लिए we need to find GM1, which is 1 milliampere per volt square into VSG minus VTH. So VSG is 12. VG, how much was VG? VSG1 is 3. 3 minus 1. 3 minus 1. So it is 2 millisiemens. GM1 is 2 millisiemens. R3 is 4 kilo ohm. So AV1 is actually 8 volt by volt. Now coming to AV2, it is GM2. GM2 we have already found out. It is, how much was it? 1.65. 1.65 millisiemen. 1.65 into R4 1 kilo upon 1 plus 1.65 into 1 kilo. And these were in milli, so units will get cancelled. It is 1.65 by 2.65, which is around 0.623. So the gain will be AV1 into AV2. That is 8 into 0.623. So which is around 5 volt by volt again. So the gain turns out to be 5 volts, or like 5 volt by volt. Now here the question is, why didn't we consider the loading effect over here? The answer is because it is a MOSFET based circuit, and when there is a MOSFET based circuit, these circuits have very high input resistance, intrinsic resistance at gate terminal. So these intrinsic resistance actually helps when avoiding the loading effect. That's why we don't see any factor of loading effect coming into picture, and the gain is actually the product of different stages. Simply it is a product without any loading factor. So this is the advantage that we get from MOSFET based circuits. Okay. Now moving ahead, here we have to find the upper cutoff frequency of our amplifier circuit. So we have two nodes, 1 and 2. So let us find the frequency at A and B, right? So frequency at node A will be 1 upon 2 pi into R0 into Cn. So we have found out Z out, right? We did find it was 377 ohms. So 1 upon 2 pi into 377 into 400 picofarad. So this frequency at A turns out to be 1.06 megahertz. Now coming back to this node B, here frequency at B we will have 1 by 2 pi into R0. So the R0 from this point is actually, since it is looking from drain node, right? And gate has infinite resistance, so it will not come into picture. Drain has 1 by GD as intrinsic resistance. Since lambda is 0, GD will also be 0, so it will also not come into picture. The only resistance that we will see is R3. Now coming to capacitances. So here C1's like M1 don't have any intrinsic capacitances, or we are neglecting the intrinsic capacitances for M1. We'll only consider the intrinsic capacitances from M2. So here what are the capacitance that we have? Here we will see a CGS, and here we will see a CGD. So here actually CGS is the capacitance that is coming as Miller capacitance. So the resultant capacitance and CGD will come in parallel to the CGS Miller capacitance. So the effective capacitance will be CGD parallel, so it will be simply added, right? CGD plus CGS 1 minus AV2, that is gain of second stage. So that is 1 upon 2 pi into, how much is the R3? It is 4 kilo ohms into CGD was 5 picofarad plus CGS is 10 picofarad. 1 minus AV is 0.623, right? 0.623. So So 0.623 is gone means 0.4. So 10 times 0.4 is around 4 picofarad. So this resistance, this frequency at point node B will turn out to be 4.53 megahertz. Now here again the same concept, since we have to find the upper cutoff frequency, we have to actually consider the minimum of the two. So F upper cutoff frequency will be minimum of frequency at A and frequency at B. So that is upper cutoff frequency is 1.06 megahertz. Moving on to the last problem for today. So in this problem we have to find the output signal amplitude for an input sinusoid signal amplitude of 100 millivolts peak to peak. So it is given that Vn is 100 millivolts peak to peak. We know the gain AV overall, which was AV1 into AV2, which was 5 volt by volt. Now we have to find Vout. Vout will be AV overall into Vn, right? So that is simply 5 into 100 millivolt peak to peak. So Vout is 500 millivolt peak to peak, or Vout is 0.5 volt peak to peak. And with this problem we are done with all the 12 problems that were decided for this particular session, and hope you have understood the problems. Just in case if you have any doubts, please feel free to contact. You can go through the YouTube lecture as well as these lecture notes that I'll upload immediately, and we can discuss them in the next class. And until then, see you all. Have a wonderful evening ahead, and let's meet next week with a new set of problems and with a new set of zeal and enthusiasm. And on that note, thank you so much, and have a wonderful evening ahead. Thank you.